Let's discuss electronegativity today. And we are actually basically discussing about periodic properties. And remember few things when we were starting the periodic classification. I told you very clearly few things. If you are good at periodic classification, then you are good at chemistry, right? Because the entire chemistry revolves around what? The periodic classification. So what do you mean by knowing periodic classification? Understand that it's not about simply placing the elements in rows and columns. It's not that simple, I was always telling you. In fact, understand that it stimulates research, and I was telling you that if any element is even found out few years from now, it has a position in the periodic table, its properties are fixed, everything has been fixed even though the element is not what found. So such importance is being given to the periodic table. You must understand this, right? So don't make it trivial. The other point which I was telling is, you know, there are several attempts made to actually place these elements in the periodic table earlier. We are not discussing all those. What is practical, what is operational, we are actually doing it. And let me tell you, till today, the Moosley's periodic table, otherwise we call it to be the long form of periodic table, is holding good, and that you must be practicing it, right? If you look into the geography of the periodic table, extreme left you have 2 groups, extreme right you have 6 groups, and in between you have 10 groups, and out of the main frame of the periodic table you basically have 2 series, which is called lanthanide series and actinide series. But remember that even though they are taken out from the main frame, they also belong to the main frame of the periodic table. Just for maintaining the decorum, they have been placed outside the main frame of the periodic table. You must understand this. When you are actually know everything about the periodic table, then I think you know chemistry. So if someone is knowing chemistry, the index for his, the depth of chemistry is knowing how the periodic table has been framed. You must understand that. The second thing I was telling is the most basic thing in the entire periodic table is basically, understand this, that all the properties, all the physical properties, all the chemical properties of all the elements that are available till date are functions of atomic size. If you ask me a simple question, that what is the difference between 25 elements that are available in the periodic table, then I would like to call simply size. So the most fundamental thing to discuss about before discussing any trends is atomic radii, and yesterday I was actually telling you the atomic radii and the difficulties we faced while dealing with an idealistic definition of atomic radii, and we didn't run away. We actually stayed back and we were telling about some operational definitions in presence of so understand, right? So such importance is given toward the periodic table. Anyone is good at periodic table, he is good at what? Chemistry, right? If that is the case, let's take up the fundamental thing, another fundamental periodic property, and that's nothing but electronegativity in today's class, and I'll go in for its applications. When I say applications, these are the questions which you are supposed to be encountering in exams, and of course the trends of these periodic properties, how it varies in a period, how it varies in a group. That's what I meant by trend, and applications are those which will be asked in exam. Right? Let us understand, let's define what exactly is electronegativity. Right? Let me define what is electronegativity. If someone is asking you what is electronegativity, first of all, tell him that it's basically nothing but a periodic property. A property which repeats itself as regular intervals in a period can be called as what? A periodic property. Now, what is electronegativity? Now, observe what is electronegativity. I just defined it. Watch carefully here. It's basically tendency. It's basically tendency. Now, why I insist on tendency? For the simple reason, because tendency doesn't have units. It's basically a tendency. It's basically a tendency. You must understand, it doesn't have units. So if someone is asking you what are the units of electronegativity, you tell him that it's simply a tendency, but it doesn't have any what? Units. You must understand. So electronegativity is basically tendency of what? Of whom? Of whom? Of atoms to attract. Remember that it's basically a tendency of atoms to attract. To attract. Attract what? Attract what? Attract a bond pair in a bond. On a bond. So you must understand this. So tendency of an atom or atoms to attract a bond pair towards bond pair, in fact towards itself, you must understand. Towards itself, you must understand this. So it's basically nothing but a tendency. It doesn't have any units. It doesn't have any units. It's basically a tendency of atoms to attract a bond pair towards itself in a bond. In a bond. So we are considering the situation where it is a bond between two atoms and one of the atoms is attracting the bond pair towards itself. Now understand, such tendency can be called as what? Electronegativity, you must understand. If this is the case, we wanted to investigate on what factors does electronegativity depend upon. It's important, right? So I wanted to put it in a sequence. See, please understand that we are discussing periodic properties. Periodic properties. And the most fundamental thing in the periodic properties is atomic radii. And if you recollect, atomic radii decreases from left to right and increases from top to bottom. You must understand this, right? Because all the physical and all the chemical properties are functions of what? Atomic radii, right? And in that case, we are dealing with electronegativity. And electronegativity is nothing but a tendency. I would like to underline this. It's basically a tendency, and tendency has no units. It doesn't have any units. So tendency of atoms to attract a bond pair. So it's all about relative thing. It's all about relative thing. So it's basically, I can call a relative tendency, right? Not an absolute one, but a relative tendency. Relative to what? The other atom also with you participating in bonding. So it's basically relative tendency of atoms to attract a bond pair towards itself in a bond can be called as what? Electronegativity. You must understand this. So if this is the case, then I can simply say this is what is found out. In fact, for your information, understand that smaller ones attract more. So this tendency is basically more if the atom is what? Smaller. So on relative basis, when two atoms are participating in bonding, then the smaller ones attract more, and that tendency, it's a relative tendency of atoms to attract an electron pair towards itself can be called as what? Electronegativity. So if I can give you an example for this, if A and B are participating in a bond, in a covalent bond, you must understand. A and B are participating. Now what if someone is asking me that what is the difference between A and B? Well, I don't think anything else, because the fundamental difference between all the elements in the periodic table is nothing but size. All the difference is only size. So that's why I said the chemical and physical properties, all set of properties shown by all the elements in the periodic table, they exclusively depend upon what? Size. And electronegativity is no different. So if someone is asking me, what is the difference between A and B? Then I would like to simply say it is nothing but size. It's nothing but size. So now understand that suppose out of A and B, this is smaller and this is smaller, and then in this bond, you give one, I give one, we both share. That's how the covalent bond is. You give one, I give one, we put it at the center, we both share such that we both achieve octet. That's the reason. That is a fundamental thing in what? Covalent bond formation. If that is the case, then out of A and B, one is smaller. And then this bond pair, which is supposed to stay at the center, shifts towards that side, where the atom is what? Smaller. Right? So out of A and B, if it is smaller, then the tendency of B to attract the bond pair, which is otherwise supposed to be at the center, then that attraction of the bond pair towards one of them can be called as what? Can be called as electronegativity. And I call this relative tendency because it is not about an absolute B tendency, because you are participating in bonding. So relative to A, B is smaller, and you can see smaller ones attract more. So what I understand basically is, I can simply say If smaller ones attract more, then electronegativity is basically a function of size. It is basically an electronegativity is a function of size. You must understand. You said on what factors that electronegativity depend upon. Well, there is only one factor in which all the periodic properties depend upon. It's nothing but size. Nothing more than that. Right? So even electronegativity is a function of size. As I have written, you can actually see smaller ones attract more. If this is the case, if you wanted to have an exact relation between these two, then I think, as I said, smaller ones attract more. So it also implies that electronegativity is inversely related to size. You must understand. Inversely related to size, you must understand this. So the smaller the size, the attraction is more. So that attraction is nothing and labeled to be electronegativity. So I have framed a function on which it's basically depending upon. Right? So understand, we are dealing with what? Periodic properties. It's basically we are dealing with what? Electronegativity. And it's basically a relative tendency, not exactly a tendency. It's a relative tendency because you're comparing yourself with the other atom which is participating in bonding with you. So it's a relative tendency of atom to attract a bond pair towards itself in a bond. That can be called as what? Electronegativity, and smaller ones attract more. So it implies that electronegativity is a function of size and both are inversely related to each other. That's what we understand electronegativity is, right? If this is the case, they both are inversely related, then understand we can write the trend. We can basically write the trend here. Watch carefully here. Well, I would like to write the trend. If you say that electronegativity is a function of size, it varies with size, and if you say electronegativity is inversely related to size, then I think in periods size decreases. Its size decreases. So electronegativity must be increasing. Right, electronegativity is increasing because both are inversely related to one another. Similarly, in groups, the size is basically increasing. So electronegativity must decrease. Right? This is what is the trend. The trend of what? Electronegativity in both periods and what? Groups. You must understand. So if you actually see the electronegativity increasing from left to right in a period, and if that is a trend, well, understand that electronegativity is the term basically used for what? Nonmetals. Because you will find the increase towards from left to right, and when it is from left to right, I think to the right of the periodic table, you will have mostly nonmetals. The entire P block is available there. Right? The entire P block is available there, and it consists of what? Non-metals. You must understand. So electronegativity is a word basically used for what? Non-metals, and not used for what? Metals, because we have the other periodic property for them. Understand that. So I come to a conclusion that the size decreases, electronegativity increasing from left to right. So basically electronegativity is told for what? Non-metals. You must understand. So what I have done here, I've taken a periodic property, electronegativity. It's nothing but the relative tendency of atom to attract a bond pair towards itself while participating in what? A bonding. So it's basically not an absolute tendency, it's a relative tendency. And I found that smaller atoms attract more. So naturally, electronegativity is a function of what? Size with an inverse relation. So if that is the case, in periods size decreases, electronegativity will be increasing from left to right. And similarly, in a group, size is increasing. So electronegativity must what? Decrease. You must understand. So all the elements placed to the extreme left, bottom has zero electronegativity, rather they are more electropositive, not electronegative. I think if you wanted to find the highest electronegative elements, they are placed to the extreme right top. You must understand. And halogens are the elements which I'm speaking of with the highest what? Electronegativities, right? That's about the basic things about electronegativity. Now what are applications? right? You cannot go on with the definition and go and write the exam what you are preparing for. So what are its applications? Let me tell you a few things here. Observe carefully here. Observe carefully. Let's see its applications, right? And the applications of electronegativity, if you actually see why it's extremely important. Electronegativity and its importance. In fact, understand this. Electronegativity and its importance. It's important, right? Now, since I said it's a relative tendency, it's basically a relative tendency, consider this. Consider a heteroatomic bond. Heteroatomic bond. Heteroatomic bond means a bond between two dissimilar atoms. Homoatomic systems are those where a bond between similar atoms. So what I'm trying to do here, I'm taking a heteroatomic bond. When you take a heteroatomic bond, let us consider a bond between A and B. A and B. This is heteroatomic because this is a bond between A and B. And this is a covalent bond. This is a covalent bond. And remember and recollect that a bond between two nonmetals is basically what? Covalent. Is essentially what? Covalent. In covalent bond, what happens is you give one, I give one, we both put it at the center, and exactly at the center lies the bond pair. That's the bond pair. The bond pair must be at the center, right? You must understand this. The bond pair is supposed to be at what? Center. And I'm trying to explain why electronegativity is extremely important and you cannot ignore it. You cannot ignore it, right? Because its applications seem to be affecting even bond energies. So understand, if I take a heteroatomic bond like this, A and B, right, assume, right, and if this is A and B, so I can theoretically say, what theory? What theory I'm actually referring to? Theoretically, in the sense, it's a covalent bond, and people told us that in a covalent bond, you give one, I give one, we both put it at the center. You satisfy the octet, I satisfy the octet, and live happily. This is what is the story. This is what is the theory of what covalent bond you must understand. If that is the case, theoretically, the bond pair exactly at the center. The bond pair at center. Right, that is theory, right? And if it is theory, what I will do, let the theoretical bond energy, let it be bond energy, theoretical bond energy, let it be EAB. Now, why there is a bond energy? Why? What is a bond energy? Bond energy is the energy released when the bond is established. Because what happens is, this atom A has no octet. This atom B has no octet. So both are deficit of what? Octets, the total number of electrons, right? Because that's important to become stable. So you are not unstable, you are not stable. So what we are trying to do is, you approach each other. You approach each other, you're vomiting energy. You're doing some work, the vomiting energy. Come close to a distance, right, beyond which the potential energy will increase. You can't move, right? The bond will rupture. So you will actually stop at a distance. When you stop at a distance, you're basically losing what? Energy. That energy must be compensated to actually remove these two back, and that's what I'm actually referring to, what? Bond energy. Energy required to break a bond. Because when these two atoms are approaching each other, the potential energy is decreasing. You're doing some work to get these two together. In the process, energy is lost, and if you wanted to break them apart, that much energy you need to provide, right? So, assuming that there is a bond between A and B, theoretically, the bond pair must be at the center. This is the bond pair. You must understand, it is supposed to be at the center. If theoretically, assuming that for a moment, that theoretically the bond pair is at the center, then let the theoretical bond energy, let it be EAB. Now, what is theoretical bond energy is, In this case, basically what we are assuming. Now, what is theoretical bond energy? I draw the attention, please. I draw the attention. What is theoretical bond energy? The bond energy when you are calculating, assuming that the bond pair is exactly at the center in a heteroatomic bond. Well, I did not say the bond pair will be at the center in case of homoatomic system, because in homoatomic system the bond is between two similar atoms, right? So anyway the bond pair will be at the center. Now in a heteroatomic bond involving A and B, theoretically the bond pair is at the center. In such a situation, the theoretical bond energy, because this is theoretical, so this theoretical bond energy is EAB. Let it be EAB, right? But understand this. Look at this case. Out of A and B, one must be smaller. One must be small. You must understand here. Because the difference between A and B is what? The only difference that is available between A and B is one of the atoms is smaller. And we were discussing just right now when I was introducing electronegativity to you that smaller ones attract more. If that is the case, then out of A and B, one must be smaller. Assume that B is small. B is what? Smaller. B is smaller. Then what happens? In the bond AB, since this is small and smaller ones attract more, the bond pair which is supposed to be at the center is now moving towards B. Is moving towards what? B. And I wanted to warn you, remember there is a shift of the bond pair towards one of the atoms towards the other atoms which is smaller. It's basically only shift. It is just basically a shift. It's not a complete, shift of electrons where the electron which is contributed by A is taken away by B. No, the electron of A remains in its shell and the electrons of B also remain in its shell, but there is a shift from the center towards one of the smaller atoms. The electrons are not leaving their shells, mind you. I repeat again, please. The electrons are basically not removed from their respective shells. It's basically only a shift. A shift can be only understood when you treat electron to be a cloud. And there is a cloud shift from one of the bigger atoms towards the smaller atoms. No one is being removed from their shells. If it is removed, that is a case of an ionic bond. You must understand. Ions are formed. It is just a partial shift of what? Electron cloud from the center towards that atom which is basically what? Smaller. You must understand. If this is the case, then if there is a shift, then the A and B, this develops a partial negative charge and this develops a partial positive charge. You must understand. Remember, I am very consciously putting partial. If it was a complete route and if the electrons are leaving the shells, I would have put the full charge. You must understand this. I would have put the full charge. You must understand it's basically only a partial charge. That means there is a shift of the electron pair from the center towards that atom which is smaller, and no electron is leaving its shells. If it would have left, then it would have been a full charge. You must understand this, right? So you develop what? Partial charges. So I can simply say poles developed. You must understand. The poles have been developed. And all this, what I'm discussing here in the case 2, all this, right? This I call theory. And in this experimental case, this is I call the experimental case, or I call the operational case. The difference between these two is this theory, see, I'm writing it, ignores this bloody shift. You must understand. This theory has ignored this shift. In theory, what you assumed is basically It's a heteroatomic bond. It's a covalent bond. Then in a covalent bond, you're supposed to share, and the shared pair or the bond pair is supposed to be at the center, and that's what you have assumed. And if you have assumed, then you will have a theoretical bond energy, let it be EAB, because bond energy will be there, because atoms approaching each other, you need to do some work, and similarly that much magnitude of work is basically required to break them apart. That's called bond energy. So what you have done is just theoretically ignored this bloody shift, what I'm telling you here. You have ignored the shift. Which shift I'm speaking of? You understand, it's the same bond. It's the same bond. But here, B is smaller. The B is small, and smaller ones attract more. Then, if they do attract, then there is a shift. This shift is basically ignored by what? Theory. This theory ignores the shift. And what happens? Then you develop a partial negative charge. I call it partial because it is only a shift of the electron cloud from one atom to the other. You're not leaving your shells. It's not an ionic bond. It's basically nothing but what? It's nothing but what? Covalent bond, you must understand. So why are you so much worried if there is a shift? You might ask this question. Why are you worried about if you have a shift? What the hell is happening? Why are you worried? And what happens to this if they have ignored the shift? So what is the worry here? Why are you worried? Then remember, if the theoretical bond energy, if you consider it to be EAB, but then experimental bond energy, remember, experimental bond energy. Now the issue is whether it is, theoretically you are telling the bond energy, or go and verify in a lab, right? Both must be same. Both must be same. After all, we are dealing with the same bond. Whether you do it theoretically, you do it what? Practically, go into the lab and measure, you expect the bond energies must be what? Same. Now, my worry and why I'm shouting here is basically understand that, if the theoretical bond energy is EAB and the experimental bond energy, we expect it to be same, but experimental bond energies seem to be E-AB. E-AB, that's my worry. That's my worry, man. Now understand that it is the same bond. It is the same bond, but the bond energies, the theoretical bond energy and the experimental bond energy, you find a discrepancy. You find a discrepancy. It's different. It's a discrepancy. It's a difference in bond energies you must understand here. There is a difference in bond energies you must understand. Right? Then that is a big issue. That is a big issue. Now basically, why did you find the discrepancy? Because you ignored the shift. This theory ignored this entire thing what we are discussing. You thought that the shift is trivial, you ignored it, and the consequence you will find it when you actually determine the bond energies. You must understand this, right? So you cannot what? Ignore the shifts, you must understand, because they have a direct bearing on what? Bond energies, which is the most fundamental thing you must understand. Right? So electronegativity, now what I mean by all this discussion is electronegativity is a serious thing. Electronegativity is a serious thing, right? If you don't consider the shifts, because it's a relative tendency of attracting a bond pair towards one of the atoms, if you try to ignore it, it will affect the bond energies, which is basically an essential thing in chemistry. After all, chemistry involves old bonds breaking and new bonds establishing. Old bonds breaking and new bonds establishing is chemistry. So, ignoring electronegativity, if it has a direct bearing on what? The bond energies, I think it is a serious thing you must be considering rather than what? Ignoring. If you try to ignore, as the theory is ignored, then I think you can see the discrepancy in the bond energies. You must understand. So when we have done this, why don't we measure something for you? Why don't we measure something for you and find out electronegativities of the atoms? Since we have done here, so why don't we do it? Right? Shall we? Yes, of course, yes. Right. Now what I will do, see, basically we wanted to know, there are n number of elements in the periodic table, and I wanted electronegativity to be fixed for each and every atom in the periodic table. Well, when I say each and every atom, it's also prudent, wise on your part, understand that electronegativity is something which we discuss for non-metals, not for metals, right? So for each and every non-metal that is available in the periodic table, I wanted to fix electronegativity. Now this relative tendency has been given. So you are telling me basically that, you know, unless two atoms are participating in bonding and one of them is smaller, I think you cannot measure the tendencies. That's what you were telling me, right? But what I will try and do is, you know, we will basically assign that this tendency, we wanted to fix this tendency for each and every atom, or each and every atom that is a non-metal, rather more considerably for non-metals. I wanted to fix electronegativity through a number. Well, I wanted to fix a number. Well, I am telling you this, I wanted to fix a number to each and every non-metal that is available in the periodic table, such that reading that number, I can actually judge the magnitude of electronegativity that is present in each and every non-metal. So what we are trying to do here, what we will do, we will basically assign a number, and let me tell you, when I say this number, and this will be without units. This will be without units. You must understand, after all, electronegativity is basically a tendency. So what I will do, I will assign a number that's without units, such that we get to know about the magnitude of electronegativity, highest or the lowest or whatever, such things can be actually exchanged when we discuss about electronegativity. That's our aim. So what we will do for this, in fact, what Pauling has done, Pauling has attempted this. Let me tell you this, Pauling has attempted this. This is the guy who's basically attempted this. Now, how did he do this? It's something like a common sense, right? It's slightly arbitrarily he has used this equation, and then he was able to assign numbers for all the non-metals that are given. So what he has done basically is, you just see here what I'm writing, right? What you do is consider a bond between A and B, and let us assume this is smaller. You consider a bond between A and B, which is a heteroatomic system, bond between two different atoms. So you have A and B here, B is smaller, so you have a shift here, right? You have a shift here, and where this shift I ignore here, I ignore the shift, and all the story what we are telling, the shift and all. Then let the theoretical bond energy, let it be EAB. EAB is nothing but theoretical bond energy. So what you have done here is ignore this shift of shifting of electrons, all this, right, that is the case. Now in the second case, what you do is, you consider the shift. This I call experimental or more operational. You must understand. What you do is, you consider this shift. Then if you consider this shift, this is the B, this is the shift, and what you're doing is, you consider this shift. When you consider this shift, let the experimental, or I call this to be observed, or the real bond energy, let it be E dash AB. You must understand, right? In first case, You're ignoring the shift, you're ignoring the electronegativity, what we are discussing. And in the second case, you have actually considered this shift, and thereby you found that there is a difference in bond energies while doing it theoretically, and there is a difference where the bond energy is real. So what Pauling is doing here, is basically what he does is, it has been observed. It has been observed. Right? It has been observed. It is observed that E dash AB, which is the real bond energy, or the observed bond energy, the real bond energy or the observed bond energy is rather greater than, right, EAB, which is the theoretical bond energy. Well, if that is the case, you have an inequality between observed bond energy and the theoretical bond energy. Well, I don't dare to ignore these two. Well, how conveniently people have ignored this shift. You're ignoring the shift means you're ignoring the electronegativity. You're not supposed to do that. If you do that, you can see the inequality clearly. Experimental bond energy is different from what? Theoretical bond energy. If that is the case, then let us make the difference. So if you actually look into the difference, E dash AB minus, because you have an inequality, right, minus EAB is nothing but delta. You'll get some value. That's nothing but delta. Right? It is joules. It is ergs. It is joules. Because after all, this is energy minus energy, you're getting delta. And what Pauling is doing is, this delta is referred to be polarity. This is what he is actually telling us to be polarity. And when this is the case, if I can define what is polarity, polarity is basically what? It's nothing but unequal sharing of bond pair. You must understand here. Unequal sharing of bond pair is nothing but what? Polarity. If he's asking in the exam, don't write any story. Do not write all this story. Unequal sharing of bond pair. Now, what do you mean by unequal sharing of bond pair? The bond pair which is supposed to be at the center, right, has been shifting towards what? B, because B is smaller. So it is an unequal sharing. Theoretically, it should be an equal sharing for covalent bond. But if it is unequally shared, that is what is called polarity. And polarity, if you wanted to know how much is the shift, right, if it is a great shift, I think this will be greater. If it's more shift, it would be further greater, you must understand. And the difference is put as what? Delta, and that's nothing but polarity. Well, there is something in the mind of what? Pauling. Now, what is there? You see, we cannot, we just wanted to know which element is what? More electronegative, which element is less electronegative among the non-metals. You must understand electronegativity is basically told for what? Non-metals, and I wanted to fix it with a number. Well, understand this, right? So if someone is asking what is the electronegativity of fluorine, then in the periodic table it is assigned a number 4. It's number 4. The most electronegative element is fluorine, next is oxygen, then nitrogen, and then the halogens come in. You must understand, right? But each halogen or each fluorine, oxygen and nitrogen have been assigned a number. Greater the number, greater is electronegativity. But the issue arises, how is fluorine given the highest number, and what is this for? Why 4 should be given? Right? For oxygen, less than 4 has been given. Right? Next, nitrogen comes. How did he come to this hierarchy? How did this fix this number 4, 3, etc. For particular elements is the issue. So, let us discuss this and come and assign ourselves, right, how he has done this. Observe carefully here. Observe. If this is the case, then understand, I just wanted to rub this and come on and assign what? A number. So understand this before I rub this. Pauling has attempted and he wanted to assign a number without units. And as I said, the first case ignores the shift. The second case considers the shift. And when you see there is a discrepancy in the bond energies and the difference is put as delta, which is referred to as polarity. And polarity is nothing but what? Unequal sharing of bond pair. Let us move ahead and see what is happening here. Now let us see what we are doing here. Watch carefully here, right? Watch here, watch here, watch. Now what is Pauling doing here? Let us assign numbers to elements. I'm referring to the atoms. Assign numbers to the elements to get electronegativity info. To get electronegativity info, we need to assign numbers. And this is basically done by Pauling. So what he has done is basically, look, take this polarity case. Take the case of polarity. Take the case of polarity here. It's nothing but unequal sharing of bond pair. That's nothing but E dash AB minus EAB, which is put to be delta, and this delta is called polarity. And this is experimental, or I can say observed bond energy minus theoretical bond energy, and the difference is put to be what? Delta. And what he has found, right, if the polarity is more, there is a common sense even, right? Is a common sense even. What he says is basically, right, the delta, delta depends on the degree of what? The shift. The degree of shift. Greater the shift, greater is what? Polarity, you must understand. Right? Greater is the shift, greater is what? The polarity. Now what is he doing is, in the case of A and B, see, look what he is doing. Look what he is doing. If this is the bond, he says, let XA be electronegativity of A. He's fixing it to be XA. X is nothing but a number. It's nothing but a number without units. Let the number assigned to A, let it be the electronegativity of A. And he also says, let XB be the electronegativity of B. So what are X's? X's are nothing but what? Numbers without units. Because it is simply a tendency. Now he has in his hand, mind you, two things here. He has in his hands this delta. For this bond, I'm considering this bond, he has found out delta and it is very much there in his hands. It's very much there in his hands, right, in his hands. He has calculated it. How did he calculate? It's nothing but the observed bond energy minus what? The theoretical bond energy, one considering shift, the other ignoring shift. The difference is delta. He has gone to the lab. He has noted down the value of the difference between theoretical and experimental bond energy of this bond AB. He came back from the lab, noting down the delta, which is nothing but polarity, which has the units of what? Joules, because the difference is nothing but what? Joules, you must understand. He came back. Now he has in his hands delta. You must understand. He has delta. Now what he is doing, he is sitting in the classroom now, in his own room, because we are out from the lab after determining delta, and what he is doing is making a simple math. That let the electronegativity of A be XA, X is nothing but a number given. XB be the electronegativity of B, then it's a common sense that if the electronegativity difference, this is nothing but This is, mind you, this is minus, mind you this. XA, this is minus, it's not dash. It's basically minus, you must understand. XA minus XB. XA minus XB is nothing but the electronegativity difference. The XA minus XB is nothing but the electronegativity difference. If the electronegativity difference is more, then the bond pair is attracted towards a smaller atom more, right? Then the polarity is more. It's a common sense. It's a common sense. So remember, he's trying to make a difference between the electronegativity numbers. Suppose if one is assumed to be 4, the other is 1, then 4 minus 1 is 3. That's nothing but the electronegativity difference. Don't take it as an hyphen, as I'm writing it to be minus for you. Then this difference of electronegativities, what he found is XA minus XB. He found that it is proportional to delta. Well, I'm not an iota surprised here, not even an inch surprised here. Not even an inch surprised here. Because if the electronegativity difference is more, the shift is more, then it will affect the bond energies obviously. Obviously, it will be affecting the bond energies. So naturally, I think you will find this more, furthermore, I think if the delta will be more, then the E dash AB will be further greater than EAB, you must understand. So if the electronegativity difference is more, then it is proportional to delta, you must understand here. And this is E dash AB, and this is the observed bond energy. And this is basically the theoretical bond energy. This is theo bond energy. And then XA minus XB is proportional to delta. And if he has actually found out, it's not exactly delta. In fact, what he found was, this electronegativity difference, XA minus XB, is proportional to root delta rather. You must understand. So, but anyway, whether it's a root delta or whatever, you must understand it's proportional to delta, indicating that greater the electronegativity difference, greater is the effect on the bond energies, and that is how he has done it. Now, if this is the case, he further proceeds like this. If XA minus XB is proportional to root delta, then what he is basically doing is, he also says it implies XA minus XB is, I remove the proportionality constant which he found out, 0.208 into root delta. This is the basic Pauling's equation. Yes, this is the basic Pauling's equation. Now, if once you have your basic Pauling's equation, what are we supposed to do? What are we doing here? We are basically supposed to assign numbers. You must be assigning numbers to each and every element, such that looking at the number, I would be in a position to judge whether it has higher electronegativity or lower electronegativity, etc. Till now we have not done that. So we have arrived at a basic Pauling's equation, which might be a question in exam, which is asked in exam. Pauling's equation is basically XA minus XB is 0.208 into root delta, where XA as is represented by electronegativity of A, XB is electronegativity of B, and delta here represents polarity. That's the difference between an experimental or observed bond energy minus what? Theoretical bond energy, you must understand. Right? Now let us assign numbers. Because we have the basic Pauling's equation. Now he uses logic. Now basically he uses logic. Now what are we doing? Right? Understand. Now this is the Pauling. Now to what he's doing is basically Pauling tries to assign numbers. Right? He wanted to assign numbers to to elements to get electronegativity info. Electronegativity info. For that, he uses logic. You must understand. Now, what is the logic here? Now, understand that this is the basic Pauling's equation. I put it here, the Pauling's equation, if you see, it's basically XA minus XB is 0.208 into root delta. This is the basic Pauling's equation, and I explained you what is XA, XB, etc. Now this is not enough. Our aim is to assign what? Numbers to each and every element to get the electronegativity magnitude info. So what he is trying to do, he picked up an element in the periodic table which almost reacts with every element in the other elements in the periodic table. And I found such elements to be fluorine. Fluorine is the element which reacts with almost every element in the periodic table. It is fluorine which reacts with every element in the periodic table, not other element. So what he has done basically is, you take fluorine. Take fluorine. So here is a logic rather. This is the logic. This is the logic, mind you. The logic used by Pauling. The logic used by Pauling is, what he has done, he has taken fluorine, and he assigned arbitrarily, mind you, he has taken fluorine, and he assigned arbitrarily, without any reason, without any experimental backing, just like that. Right? He has taken fluorine. The fluorine, why did he take? He didn't choose the other elements because he wanted an element such that it reacts with most of the elements, and fluorine is the guy who reacts with every fellow in the periodic table. So he has taken fluorine, assigned arbitrarily. Arbitrarily means without any experimental backing or background, right? Assigned a number 4. Now don't ask me why number 4. You need not ask because it is arbitrarily. You can put it to be 10. If you put it to be 10, it will be your scale and not Pauling's scale. Pauling has taken 4, and without any reason, experimental backing, he has taken to be 4. It's arbitrary. You can take any number. He would have taken any number rather. He would have taken any number. But he has taken number what? 4. That's arbitrary without any experimental background. Right? And he number 4, that means that it implies in the XA, this is fluorine and this is XB. That is fluorine and XB, and then this is equal to 0.208 into root delta. He has fixed the XA to be fluorine and with a number 4. So XA is 4, XB, it remains that way, and this is the equation what he has. Now what he is trying to do, since fluorine reacts with each and every element in the periodic table, so what he is doing is, he is changing this. He is basically changing XB. Like this fluorine remains and this is H. This fluorine remains and this is oxygen. This fluorine remains and this is nitrogen. And you know, this number of fluorine is fixed. This is 4. Right? He's trying to assign number to this, and is continuing because fluorine reacts with almost every element in the periodic table. Now, if you consider this, for this, he is finding EAB, E-AB. For this, he is finding EAB, E-AB. The difference is delta. Then he is substituting here in this equation. Suppose if I consider this, he is basically finding E-HF minus EHF, and this delta is found out, and substitute here. When you substitute here, then what you're getting is, this is 4, it is given 4 minus XB is equal to 0.208 into root delta. The delta is found out with the difference of what? The bond energies, substitute, and then XB can be found. XB can be found. Similarly, he is rotating this hydrogen with oxygen, oxygen with nitrogen. This fixed, this is 4. And what is very, very important, what he has found in this entire observations is the values of H, oxygen, nitrogen, or any other element was less than 4. Less than 4. So, fluorine is given 4, that is having a maximum electronegativity. Maximum electronegativity. So if you see the electronegativity trend through the Pauling scale, I think fluorine has the highest, then comes oxygen, then comes nitrogen, like that, and he has given a number 4 for this. And remember, oxygen will be having a lesser value than fluorine, because fluorine has the highest value of what? Electronegativity. Well, understand the logic I would like to say. This is the Pauling's equation. What he has done, he has taken fluorine and assigned arbitrarily a number 4. So this is number 4. And he's trying to rotate XB. Suppose if this is fluorine given 4, hydrogen, the HF, he's trying to find out E dash of HF, EA of HF, and find delta. Substitute in this equation the delta, and since this is 4, you can find out XB, and that's how he has found out for the other elements. And he was able to what? Assign numbers to elements to generate electronegativity what? Information. You must understand this, right? So that's the basic Pauling's equation. And remember, he has done this, and as I now, we've now seeing the numbers. I think the numbers are actually printed in your textbook. They are actually printed in your textbook. Seeing the number without any units. This is 4. This is basically 4. This is 4. And mind you that the 4 has no units. It doesn't have any units. You must understand. It is just 4. It is just 4. Right? It's a tendency. You must understand this. So if I can explain this properly to you, what he's trying to do is to assign numbers to elements to give electronegativity information. Right? And this is the Pauling's equation. In this, he has chosen an element fluorine. The reason why he has chosen fluorine is simply because it is fluorine which will react with almost every element in the periodic table. So what he has done, this fluorine is fixed with a number 4, and his XB, he's trying to find it out, because this is the electronegativity of XB, XO, XN, and the difference is found out delta, and you substitute here, and then you are supposed to get the electronegativity difference. And what he found is very strange, and in line with his expectation, not strange rather, that each and every element, the other elements other than fluorine, have electronegativities which are lesser than what? 4. So highest is 4, remember. Any value lesser than 4 is having a lesser electronegativity, and in the process you can see the highest is fluorine, next comes oxygen, next comes what? Nitrogen, and so on. And remember, electronegativity is only told for what? Non-metals. Now you can sit, relax. If you're missed out on anything, please revise and see, right? And you can see there that I have explained it, right, the theory in depth for you. If any doubts, you can revise, relax, and then we will get into the next periodic table, next periodic property in the next class.